In May 2023, the world watched as Microsoft made history, signing the first ever commercial contract to purchase electricity directly sourced from nuclear fusion, a dream pursued since the dawn of atomic energy. The startup chosen was Helion Energy, fueled not just by over $1 billion in funding and the Midas touch of Sam Altman, but by headlines promising a new era. Pundits called it a turning point, but history, as it turns out, is written by more than headliners. By 2026, the fusion race looked very different. Behind the excitement, hard science was quietly redrawing the boundaries. That year, physicist Carl Lackner published an unassuming but seismic paper in the Journal of Fusion Energy. The target, Helions' own official data and claims. Lackner's verdict, using Helions numbers, was unkind. The laws of physics, not budgets or brand, decide fusion's fate. And those laws said Helions' approach could never produce net energy from the deuterium, helium-3 reaction. The system lost more energy to physics than money or engineering could ever recover. Meanwhile, away from the spotlight, a team led by Dr. John Brandenburg and Kepler Aerospace was designing a machine governed from day one by the real thermodynamic requirements. Their company, American Fusion, ticker AMFN, built what the science actually demanded, a device called the Texatron. While others talked, they calculated, cited, built. Soon, their story would force the world to rethink the fusion race. Fusion itself is simple in theory. Fuse two light atomic nuclei, and the resulting reaction releases immense power, as every star in the sky attests. On Earth, we have spent decades trying to control this process. The immediate challenge has always been containment. At fusion conditions, matter becomes a plasma, a wild mix of ions and electrons hotter than any solid can withstand. The problem is how to hold, for even a heartbeat, this burning cloud so energy can be harvested. But as the field matured, physicists uncovered an even more fundamental challenge. To win net energy from deuterium, helium-3, a clean fusion fuel, the heavy ions, the actual fuel, must reach temperatures vastly higher than the surrounding electrons. If the ions are the furnace, the electrons are ambient air, and the gap between them is non-negotiable. It's not a design preference, it's a requirement written in quantum possibility. Here's where the Spitzer equilibration rears its head. This is the iron law that electrons and ions, bouncing off each other billions of times per second, try to equalize their temperatures. Every collision leaks energy from the crucially hot ions into the lighter electrons. As the electrons heat, they radiate energy right out of the plasma as X-rays, draining the system faster than fusion can resupply it. This barrier, called the Bremsstrahlung death zone, has quietly doomed every machine with pulses too long or conditions too gentle. Helions' own CEO, David Kirtley, argued they could outrun this, firing pulses fast enough that the Spitzer clock would not have time to reach equilibrium. Lackner's rebuttal was definitive. Helions' pulse lasts under a millisecond, but even that is tens to hundreds of times too long. The energy that builds hot ions is siphoned off by electrons long before the pulse ends, based on fundamental plasma physics. American Fusion's Texatron, instead, fires at a radically different pace. Like an engine producing thousands of tiny controlled explosions instead of one sustained burn, it strikes the fusion plasma with 1,000 hammer-like pulses per second. Each fusion burn window lasts barely 20 to 25 microseconds, a 40-fold advantage over Helion.